For whatever reason, I'm not doing well with technology today. I like to think I'm good with technology, but I guess what I think and how I actually do, I guess, is two different things. Where I can tell you it works at home. I bought a new computer, so because the old one's getting, it was annoying. The Y button stopped working. So just like, and the computer was over 5 years old. I was like, I should probably buy a new one. It's like, if I need a sign, that's a sign. So I bought a new computer and I got it to work at home. And of course, when I come here to class, it doesn't work. So specifically what I mean work is have the iPad connect to the computer. As they say, the show must go on. So I'm just going to talk from my completed notes that I have on the internet. So and I do need to check everyone's clearances. I know I didn't do that coming in, and don't worry, Zoom, you don't have to check. So you just see the green screen. You got it. All right. I see you see the green. Okay, see the green. Okay, good. All right. So, any questions before we start? Okay, so I know we're a little behind. It doesn't help that I'm arguing with my computer, but we're still in chapter 1. And so we're bouncing around topics quite a bit. And now I'm going to talk briefly about the metric system. So the metric system is an engineered system, and compared to sometimes what everyone else calls American system or the imperial system, where it's foot, pounds, miles, that kind of thing. So yep, here, clearance. Yeah. So, well, it's nice. What's nice about the metric system? So if I forget who here is going to be an engineer. We got some engineers in the room, right? So whenever there's something called a Jacobian. That's it's when you transfer units and whatnot on either an integral or you just transfer units. What's nice about the metric system? It's all factors of 10. Makes it real easy. Jacobians, they also use those when you change coordinate systems. So, but that's what's nice about the metric system is it's engineered. And it's actually changing. There's some discussion about it changing right now. Okay, it's green. It's good. So we have some base units. For length, we have the meter. For mass, we have the kilogram. The kilogram is something that might change. Kilogram right now is literally a block of platinum. And the problem is it's evaporating, it's changing. So we talk about changing the kilogram to a mass of silicon, and also the mole. The mole, which we'll learn about either this class or next class, is based off of carbon-12. It's based off of carbon. We're actually thinking about switching it to silicon. Time, second. Temperature, Kelvin. Electric current, amp. Amp is also the charge of 1 coulomb per second. And luminous intensity, candela. No one uses candela anymore. So nowadays, we talk about light in terms of energy. And there's also derived units. So for instance, so in physics, you might learn about a Newton. A Newton is, so second law of force is mass times acceleration. Kilogram mass times the second derivative of length, meter per second squared. So kilograms times meter divided by second squared is a Newton. And then things like a joule. A joule is a Newton meter, so kilogram. So it's mass, length squared divided by time squared. And then a watt is same thing as the energy, the joule divided by time cubed. So I'm just kind of briefly going over this because I know I'm a little behind, and I don't want to spend too much time on this stuff. How you doing, Zoom? Are you guys feeling all right? Okay. All right. So now there are two types of properties: intensive and extensive. Intensive, it doesn't matter how much stuff you have, it's always the same. Extensive, it matters how much you have. So mass is an extensive property. So if you look at water, so I got my 40-ounce water bottle here. The 40-ounce water bottle has a mass of about 1 kilogram. So that's the mass. If I'm just gonna, I'm gonna use a drink. I just drank probably about 10 milliliters. That has a mass of about 10 grams. So that was about 10 grams of water I just swallowed. So what about the density? The density of the water in this is about 1 gram per cubic centimeter. So that's the same density that's in here. That was in the 10 milliliters I just drank. That's in the entirety of Lake Tahoe. If you've ever been to Lake Tahoe, that's all fresh water. It's a huge lake. Has the same density as all the water. As long as it's not seawater, it has different. But all that water has the same density. So that's intensive. So let's go to example, calculating density. So a man receives a platinum ring from his fiance. Before he does this, he knows the weight, the ring feels a little light. So he decides to calculate its density. So density is mass divided by volume. So it has a mass of 0.315, displaces 0.233 cubic centimeters. A cubic centimeter is the same thing as a milliliter. Is the ring made of platinum? So look at the density of platinum. So mass divided by volume, and he calculates it out to be 13.5 grams per cubic centimeter. And the density of platinum is actually 21.4 grams per cubic centimeter. So from that, this person could determine that the ring, in fact, was a fake. So there's a legend, I don't know if you've heard this, about Archimedes. You've heard of Archimedes before? He was, he's a philosopher, and the king gave some gold to a goldsmith to make his crown. And the king was always wondering, like, did I get cheated? Did this goldsmith just, swipe some of the gold for himself? So he asked Archimedes to think about it. And according to legend, Archimedes was sitting in his bathtub thinking about it. And he thought about displacement and density. And he got so excited that he ran out of the bathtub, found any clothing to tell the king. So that's how legend has it. So, but that's the same idea here, using density for that. Okay. So how are we doing so far? Questions? Okay. Next thing we'll talk about are significant figures. You talk about, usually people talk about this more in lab. I don't know, I'm not teaching lab this term. So do you guys talk about this in lab at all, sig figs?
Yeah.
So you are getting this stuff, okay. So a significant figure, it tells you how well you know a measurement. So some measurements are really, really exact. So for instance, so a lot of conspiracy theorists, we never went to the moon. I don't know. When the astronauts went to the moon, we placed mirrors on the moon. Okay, and every once in a while, I think 4 times a day, we shoot a laser to the moon. And then by the light, bouncing back, we determine the distance between the Earth and the moon. And since we've been doing this for decades, we've discovered that the moon is actually moving away from us slowly, on the order of a few centimeters per year. So, but I mean, so we have a laser that does this, that's really, really precise and accurate. So I didn't talk about precision and accuracy. Accuracy means how close you are to the real number. Precision means repeatability. So the more repeatable something is, the more precise it is. So the laser method to figure out how far something is, that's very, very, well, at least we can tell how close something is to a very, very small amount of digits. Then I have my odometer on my car. Okay, my odometer in the car works by 1/10 of a mile. So So the odometer in the car is not nearly as accurate as the laser that we're using to image or to figure out how far away the moon is. And the way that significant figures work, we'll go over the rules of what's a significant figure and what's not. So this number right here, 5.213, the last one, last digit here is an estimate. We're not really sure. We're not really sure about this one. It's plus or minus probably 0.1. I'm sorry, or a thousand. I'm sorry, a thousandth. It's probably somewhere between 5.212 and 214. It depends on your measurements, but this one is kind of sort of in the right direction. So, and for instance, when you do measurements, so if you look at this measurement right here, and again, this is, hopefully you'll learn a bit of this in the lab. This is hard to see this bit, it's easier on a retina display, go figure. There is this part here, this is called the meniscus. So this only works because of the attractiveness of the liquid and the vessel. So this is probably most glassware in lab is Pyrex, is borosilicate, and it has hydroxide groups, and water, we'll learn later, is a polar molecule. So water actually has an attraction to the glass, and because it draws it up the side, and that's known as a meniscus. If you ever use plastic glassware, you'll notice there's no meniscus. So I used to use lab kits for distance labs, and when I was playing out the lab kits, I'm like, oh, there's no meniscus. That's weird. I'm like, oh yeah, it's plastic. Makes sense. So yeah, question.
Which one gives you the more accurate reading?
Well, if it's calibrated, it gives you the best. But it's the meniscus. I mean, which one gives you this? Pipettes are going to be far beyond. But if you can, there's certain tricks that you can do to make it better. It just depends on how it's manufactured. Okay. So there is no advantage to one over the other, to be honest. Mm-hmm. So you go by the bottom of the meniscus, and so this would be 4. So this would be 1, 2, 3, 4, 5, 4.5, and then you look here, and then you kind of guess. I'm going to say that's 4.57. Did I say 8? Okay. Yeah, I said before I guessed 8. So it's going to be 4.587 plus or minus 0.01. So I mean, the last digit is kind of an estimate when you're doing this as far as measurements. And same thing with temperature scales. So you can see here, this is going to be 100, 1, 2, 3, and looking here, 103.1-ish degrees Celsius. So this is a thermometer. So this is what I mean by I'm pretty sure this is about 103 degrees Celsius, but the last tenth of a digit, I'm a little shaky on. So that's what you mean by significant figures. You're like, okay, you're good to a certain amount of point, certain amount. And so something about me, my PhD advisor, he's in his 80s, and it's interesting to hear him tell stories. He talked about when computers came over into science, and like people used to pride themselves on how well they could like read glassware and read instruments, because everything was analog. Then it switched to digital, and suddenly computers just get all these sig figs, and people were just like, my special ability is gone. It's been taken over by computers. So I mean, of course, nowadays it's very unlikely that you're going to be sitting there doing this, except for Chem lab, that kind of thing. So there are a few instances that you might have to do this, but of course, this is another thing that computers do this for us. But we as humans, we still interpret the data. So that's with measurements. So here are some rules with significant figures. So all non-zero digits are significant. So interior zeros, they're significant. Leading zeros are not significant. And sometimes you can get rid of that just by using what's called scientific notation. And trailing zeros, so after a decimal point, are just significant. Before a decimal point are always significant. Before and a non-zero number are significant. And trailing zeros before an implied decimal point, they're ambiguous. So this is one of those, we don't know. And sometimes people put a decimal point in places. So let's look at these examples. So all non-zeros are significant. So this one here, 28.03. These are of course significant, but then of course we learned the interior zeros. This 0 is significant as well. So prior number. So you have 0.0032. These are not significant. So this is 0.0032. This has two significant figures. And 406, this has one significant significant figure. So if you have trailing after a decimal point, these are significant, as are these, and the interior zeros are also, well, that was already mentioned. These are significant and implied. So if you have 1200, this is you don't know. You don't know how many sig figs there are. This tells you exactly. 1.2 times 10 to the third, that tells you it's 2, and this one here tells you it's 4. If you have this period after it, that implies 4. But it's also, watch out with your English though, if it's the end of a sentence, then that's even more ambiguous. So we try to keep it in scientific notation. So how are we doing so far? Questions? Okay, what about exact numbers? So if I tell you I have 10 fingers, does that mean that my number of figures has 2 sig figs? And the answer is no, that's infinite. There's an infinite number of sig figs in exact numbers. Also, certain relationships have infinite sig figs. So I mentioned the metric system. What's funny about the English system or American system, whatever, imperial, an inch is defined as 2.54 centimeters exactly. So 2.54 centimeters being an inch does not have 3 sig figs. That has the number of significant figures that we have in the definition of a meter. So our number systems, I told you that there's actually significant figures involved in them, and that's why also they change. One of the reasons why we're looking at the moles and the kilograms, because we need more sig figs. So we're changing our definitions. Probably, I thought it was going to happen by now, but I guess not. All right, Zoomland, are you seeing me move around the screen? Is that, because I remember I looked at the video last, okay, okay, cool. And how many sig figs in each number? So 0.04450. So this initial 0 here, I know, I'm sorry, it's scribbled out. That one is not. And then there are 4 sig figs in this. And then 5.0003. So these 3 zeros are significant, and so are the 2 numbers. So this one has 5. 10 decimeters equals a meter. This is an exact relationship that has an infinite number of sig figs. 1.000 times 10 to the 5th seconds. This one has 4. So this is scientific notation. It tells you there's 4 there. So 0.4 zeros, 2 millimeters. So these 4 zeros are not significant, just the 2. This measurement has 1 sig fig. And then 10,000 meters, this is ambiguous, you don't know. So if it was 1 times 10 to the 4th meters, that would have 1. If it was 1.0, that times 10 to the 4th meters, that would be 2, and so on. But 10,000 meters, we don't know. This is ambiguous. Questions? No, that's infinite. That's a relationship. Because 10 decimeters, so deci means a tenth, right? So 10 tenths of a meter is equal to a meter. That's an exact relationship. So that when you have exact numbers. Exact numbers have no uncertainty and do not limit the sig figs. So this is an exact number. Does the fact that you have 2 eyes, does that only 1 sig fig? No, that's an infinite number of sig figs. Does the relationship, I don't know, 5,280 feet in a mile, is that 4 sig figs or is that an infinite number? That's an infinite number. So when you have exact relationships, so 12 inches in a foot, that's an exact relationship that has an infinite number. So, other questions? Okay, and so when you do calculations, so sig figs are calculations, and they're not usually as, I'm going to give you some that are examples that are really hard, but you will probably never run into them. So when you do multiplication division, the result has the factor has the lowest sig figs. So for instance, here, first number has 4 sig figs, second number has 5, third number has 2. When you do your calculation and at the end, you round it to 2 sig figs because you're limited by the 2 sig figs. And when you do addition and subtraction, you are bound by whatever value is the lowest. So if you have 2.345, so if you have this 2.345 plus 0.07 plus 2.9975, the problem is we don't know the digits after the 0.7. So because of that, you round up or round down to that hundredths place at the end. So remember, sig figs are a way of telling you how well you know the measurement. You can't say with certainty, well, this is 2.4125. You are not certain about the 25 10,000ths place. So these numbers you're not sure about. So you can't report them. At least, you shouldn't report them. So what do I mean by that? Well, I told you about the laser, right? So what if I measured, like if I say, oh, what's the distance between my house and this classroom? And I go and let's say that I have the laser thing and it tells me, okay, within a millimeter using the laser technique, I can tell you that between here and the right in front of the library, it is 3.50007 kilometers or something. And then I go, okay, well, I'm going to go from then the library, and I'm just going to count, using my feet. I'm going to all right, well, I know my foot, or I know my pace is about 1 meter, so I'm going to go and count out meters with my feet. And I could probably do that, with an accuracy of 5%. And I come back and well, it's about 200 meters from here to the library in a straight line. I can tell by pacing it out. So then, since I know the laser technique down to millimeters, I'm just going to add those together. And the answer is I can't do that because I can't measure millimeters going like this, right? I can maybe get 1/10 of a meter doing that, but it wouldn't be accurate and or precise to take those two measurements and say, you know what, I can pace out the same distance, the same way that a laser can tell distance. So that's the whole point of this, is that we have two different types of measurements. So we only know something so well. And that's, part of science. It's actually, have you ever heard of the Dunning-Kruger effect? It's kind of like the Dunning-Kruger effect quantified, if you've ever studied that. Okay. So let's do an example. Let's look at this right here, 1.10 times 0.5120 times 4.0015 times 3.4555. So we have 3 sig figs in the first one. We have 4 in the second. That's trailing 0. It counts as 1. We have 5 here, and we have 5 here. So 3 is the lowest number. So when we calculate it out in our calculator, we can only report the 3 sig figs here. So even though I know our calculator can get more digits, but with our measurement, we're only sure of so many. Is this making sense? Okay. So then same one here, 0.355 plus 105.1 minus 100.5820. We are only sure to the tenths place. So if we carry out the math, we can only report to the tenths place. Question, yeah.
And that's only because of the second number there.
Yeah.
There's 4.
Yeah, it's not the number of sig figs. It's just for addition and subtraction, it only matters for how much you know that.
I'm certain about it.
Yeah.
I'm certain.
Yeah, the certainty is, and it's the lowest that you're certain to. And it's, yeah. Other questions? Yeah, that's the lowest number, whatever you're multiplying and dividing, whichever one of those has the lowest number of sig figs. And addition and subtraction, you go by the lowest unit that you know. Well, not unit, lowest decimal or what's the other way, power, number that you know. We talk about decimals here on chemistry on Earth. If you're talking about astronomy, you're probably talking about, powers, whatever it is you're measuring. So if it's the mass of celestial objects or mass of butterfly wings, whatever it is you're looking at. So now here's a trickier one. So you have 4.562 times 3.99870 divided by the quantity 4.526755 minus 4.52.33. So remember the rules. So with order of operations, you do the parentheses first, then addition and subtraction left to right, then addition and subtraction left to right. But since we have parentheses with subtraction, we do the parentheses first. So we have to carry out this operation first, and we get the number 0.34. Is that right? It's a point. Should it be 5.4? I don't know. Well, anyways, you carry this out, and it's 52.79904. If you carry out this operation, you get that. And the problem here is we're only sure to, I'm sorry. I'm sorry. I was reading too far. I'm sorry. Here, you carry out this operation, you only know this operation is 0.03455, but you only know to the hundredths place. So you can round this up. So you can round this up to 0.35. This is 0.3455, but you only know this at 2 points here. So then you have to carry this out. When you carry out this multiplication, you have to report then your number to 2 sig figs, because this subtraction operation dropped your sig figs down to 2. So this dropped it to 2. Then when you multiply it through, you have to report the answer with 2. So does that make sense? Question?
When you round like step by step, right? Or
Yeah.
Where should we round at the end? Because for this number it'd be 0.35, or you could leave it at 0.34.
You can round at the end. It's probably better to round at the end because that's a good point. Yeah, it's because if you round as you're going, you incorporate something known as a truncation error. So it is best. That's a good question. It's best to round at the end.
Okay.
So if we're reporting the answer and it's asking for sig figs, and we got 52.79 because we can use the 2 decimals, and we rounded to 53, wouldn't that be like not accurate?
Well, by the rules of sig figs, that's all that's as well as we know it. I mean, yes, you are losing accuracy, but if you don't do that, you incorporate a systematic error into your measurements, and that can balloon up over time. So it's our way of saying we know for sure that the answer is 53. So if you report it as 52.79 or 52.80, you're not so sure about that 80. So Because I mean, so much of science is saying like, we know that there's this much. It's like other things. If you're measuring the bacteria count in the lake, like, well, when you're going to report a number, you want to make sure that you're reporting a number that's accurate, especially if it means like, well, do people swim in it and get sick, or do people swim in it and not get sick? So it's nice to be able to say things with a certain amount of accuracy. If you're borderline, like, kind of thing. So, and we have ways, and the nice thing about sig figs is we have ways of knowing how accurate it is, and you get that in reports. I remember there's a lake that my family and I like to swim in, and we always get the bacteria count before we go. We get the E. coli count before we get in, and like it was like 125 is acceptable, and the answer was, and they said, you're getting a bacteria count of 29.17. I'm like, well, if it's 29.17, 120 is okay. Like, I know for certain I can swim in this lake, kind of thing. So the numbers tell you something. Yeah, question.
So we do the calculation, and do we include those last two? Like for the one in the parentheses, we got 0.3455. Do we include all 4 digits in the calculation and then just go to the second?
It's best to keep it in and then round at the end.
Okay.
Yeah, because otherwise that you can incorporate the truncation error. So there's actually, there's a problem with certain programs, like Excel has truncation error in it, and so do calculators. Actually, so I mean, they don't carry out the digits to 10 billion each time. They truncate it. And actually you get numbers that drift over time. That's a known issue with Microsoft Excel. So
are you trying to tell me that 52.79904 is less accurate than 53?
Well, it's 53 we're sure of. So with the number C, when we do that calculation, we can tell you that we are certain that the answer is 53. If I tell you,
why isn't it 52?
it could be. I mean, whenever you have error associated with a measurement, usually it follows a standard deviation. And have you seen this before? And you say plus or minus something, it'd be 53 plus or minus 1. Typically speaking, that means that 68% of your sample size is within 1 standard deviation of 53.
Okay.
And
okay.
then 2 standard deviations would be, is it 98%? I think.
Okay, I get it now. When you relate it to standard deviation, I get it.
Yeah. So that's kind of an advanced topic for this class, but asked and answered, Your Honor.
Okay. Move forward.
Yes, ma'am. So, all right, next problem, unless there's any other questions. And I'm glad that you're asking questions. So now you have 14.84 times 0.55 minus 8.02. So it doesn't matter, this is in parentheses, but it doesn't matter because multiplication is before addition, subtraction anyways. So you carry out the multiplication here, and notice that this is to 2 sig figs. So when you do this measurement, when you do this calculation here, it brings you to 8.1. And we are sure for the 8.1, and then you subtract 8.02. Now the problem is, well, this is one with the multiplication that you should drop the 0.62. That's not a number you should keep. So actually you should drop. I mentioned up here when you have the addition and subtraction that it's sometimes it's best to keep the values. This one here, you should drop it and then do the subtraction operation and you get 0.0142. But since you're only sure to the 10th place in the multiplication, your answer is only 1 sig fig in the 10th place. So I know that this is kind of an advanced, you're probably not going to see this very often, but I'm telling you now just because, like, okay, if you see it in the future. So I'm really kind of pushing it down your, down pat so you know what this is. Any questions so far? Okay. I already mentioned, oh, I forgot log and exponents for order operations. Okay. And general problem solving. So you're going to be doing lots and lots of problem solving in class. And I mean, I mentioned before, most everyone here are here because this is a class requirement, And if I see you 10 years from now and you tell me, Mike, I remember that a mole is 6.02 times 10 to the 23rd. Like, aren't you happy? I'm like, that's great. I'm really glad you remember what a mole is. But if you came and say, Mike, what's great about your class? I learned how to attack problems and it's helped me in all my classes going forward. That would make like my teacher week or even my teacher month. I'm like, oh my gosh, I've done my job. People have taken my class and they've learned the logic on how to approach and solve problems. That's what I honestly feel like I'm teaching. I mean, of course I am teaching you chemistry, but I'm teaching the system, I'm teaching the science, and part of this is general problem solving, how to attack a problem. I even use that, I guess I'm using violent language. We attack the problem. So what do you do when you attack a problem? You sort, you look to see what information is given and also what is asked. And also in sorting the knowledge, you also have to figure out what's needed and what's not needed. Sometimes you get extra knowledge and it's irrelevant. So that's another thing with sorting knowledge. Some knowledge is irrelevant. So like, yeah, I got this measurement and my dog has fleas. The fact that your dog has fleas has nothing to do with the measurement. So sometimes you'll see this in problems. They'll give you extra information. You wonder why they give us extra information. So you can sort out what you need and what you don't need. So you strategize how to solve a problem, then you solve the problem, and then you check to see if it makes sense. So, with, I guess, the strategize and solve, specifically how we're going to do this class, we're going to use quite a bit of something called dimensional analysis, where you look at the units. So if for most of the problems in this class, solving it, we can do most of the problems via dimensional analysis. Some of the problems we have to do solve equations, like we talk about ideal gas law, you have to solve equations. But we're going to do a lot of unit conversions in this class over and over and over again. And then we check, does it make sense? For this class, if the units all work out, it's probably fine. For other class, as we go more advanced, another trick you can do is something called order of magnitude calculations. You can kind of guesstimate answers and see if it works in the ballpark, and then kind of have it in the back of your mind, like, oh, the answer should be around 10,000. If you get 12,000, you're like, okay, that's right. If you get like 20, you're like, ooh, I did something wrong. That's when you think, did I put the numbers in the calculator properly? So that's what you mean by check. Does the answer make sense? So that's also kind of like if you've ever gone to talk to someone in office hours, it's like, well, this is my answer. Like, well, professor, like, does it make sense? Like, is it right? Like, does it make sense? You're like arguing back and forth. What do you mean, does it make sense? You have to look to see like, all right, is this the answer that I kind of expected? Did I measure out, like, what's the mass of one silicon atom? And I got, something the size of the moon or Texas. Like, all right, I found out that the mass of a silicon atom is equivalent to the size of Texas. And, well, does that make sense? And the answer is no, it does not make sense. At least it shouldn't. So atoms should be very, very tiny, for instance. That's what I mean by does it make sense? Okay, so here are just a couple of them. So convert 1.76 yards to centimeters. So 1.76 yards and a meter to 1.094 yards times 100 centimeters per meter. So 1.76 yards are in fact 161 centimeters. And so I know I'm sorry, whatever reason, my laptop and my iPad decided not to communicate today. I guess I was clever enough to put different marks on this though. So notice something, we are multiplying by 1 twice. The way that we solve this problem is we've multiplied it by 1 twice. So a meter is in fact 1.094 yards. And 100 centimeters is in fact a meter. So we've solved this problem by multiplying 1.76 by 1 twice. and had the units cancel. So notice that the yards cancel and the meters cancel, and we're left with the units that we want, 161 centimeters. And does this make sense? Well, a yard is about a meter, but a meter is slightly longer. So we'd expect then the number of centimeters to be slightly less, like we'd expect it to be slightly less, like at least lower by a factor of 100. And that is what we see. So that this answer does make sense. So that's what I mean. Like, does this answer make sense? If I got the answer and I said 1.76 yards is 300 centimeters, you're like, all right, it's something wrong. So that's when you like kind of go back and check. So another one here. So 1.8 quarts to cubic centimeters. So, and I oftentimes do this. I guess I like doing this because it's neat. I a lot of times make grids. And part of it is because my undergraduate's in chemical engineering, and they give us that green engineering graph paper. And I just went with it. So you'll see me sometimes do grids like this. The grid and the multiplication are the same thing. So that just, for me, makes it look better. So 1.8 quarts and multiply by 1, a liter per 1.057 quarts, milliliter, 2 liter, 1,000th of a liter, and then cubic centimeters and milliliters, same unit. So you notice here the quarts cancel, the liters cancel, and the milliliters cancel. And then you get the answer there. And it's, we have 1.8 quarts, 2 sig figs. So then we report the answer with 2 sig figs. So questions? Do you have a question? No. Questions? Good. It is harder to read people's faces with masks on, but it's your eyes do tell a story. Okay. So calculate the displacement. So, if we have a 5.7 liter engine, so that's like a big truck. What is the volume of that in cubic inches? So if we want to change units, so same idea. We have liters, and like, so I guess I should strategize. I want to go from liters to cubic centimeters, and I need to find a way to. So if I'm going to go from liters to cubic inches, I need to. Well, I remember I mentioned before an inch is 2.54 centimeters. I need to bring my units of 5.7 liters into cubic centimeters. So, question?
I thought milliliter was equal to centimeters cubed.
It is.
Okay.
Yeah. So 5.7 liter, we can carry this out, and it's going to be 5,700 cubic centimeters. Now look at it this way. But so an inch, though, 1 inch is equal to 2.54 centimeters. But since the centimeters are cubed, we have to cube the relationship. So is that your question?
I think I just read it wrong, but yeah.
Yeah. So when you do unit conversions involving exponents, you have to cube the whole expression. So an inch is 2.54 centimeters. But since you're doing volume versus one length, you have to cube the relationship. And also you can see the units have to work out. So you have to get rid of cubic centimeters. So you have to convert it to cubic inches. So units then all cancel out. And that's one nice thing about the dimensional analysis. If you get the units all working out at the end, you know you probably did it right.
And I have 3 sig figs for that answer?
You would, yeah, 5.70. Yes, you have 3 sig figs for the answer. So it's going to be 348. So these are infinite numbers here. These are infinite expressions. So, other questions? I'm not, that's something I'm not going to make you memorize. So I guess I do apologize. I mean, I've done this so much that I don't even think, like a milli means 1,000th. So there's 1,000 thousandths in one. So I didn't even mention some of the words. So deci means 10th, centa means 100th, A milli means thousandth, micro means 1 millionth, nano means 1 billionth. Pico is after nano, then it's pico, then it's femto, then it's atto. So each one by 10 to the third. And then the other way around, oh, there's the other.
In the planner, they have the conversion.
Okay. Yeah. All the tests and all the homework are open book. So this is something you can look up at any time. So the other way around, so 10 is deca, 100 is hecta, 1,000 is kilo, then it's mega for million, mega, giga, tera, penta, exo, I think. I forget. I usually don't deal with numbers that big. Chemists tend to deal with small things. So, but yeah, you can look those up. And that's the units of 10. No one tends to use deca or hecta, except for a hectare. Hectare is used instead of an acre in Europe and everybody except for America. A hectare is 100 square meters. And also deca, some places you buy produce in decagrams, kind of like we do with pounds and ounces here in the States. So in Hungary, I used to live in Hungary. Hungary, you bought things in decagrams. So you would say like oot deca, that's 5 decagrams. So that'd be 50 grams. I guess there's a Hungarian in one of my online classes. She was all excited. I live in Hungary. Okay, other questions? All right, you can also use, this is one example using density as conversion factor. So 747 has 173,231 liters of fuel. So if the density of the fuel is 0.768 grams per cubic centimeter, what is the mass of the fuel in kilograms? So this is one, well, the density, we've measured the density down. This is not an exact number. We know this number here to 3 sig figs. But so we're gonna attack this problem. We're giving volume of fuel. We're also giving the density. The density is in grams per cubic centimeter. So looking at that, like, well, as you're tracking this, approaching this problem, the first thing you're thinking, okay, I'm going to set up my dimensionality analysis, but I'm giving the units and I'm giving cubic centimeters and the other. First thing I'm going to do, like, you know what, I'm going to have to go ahead and convert the units. And they're like, okay, well then let me put the numbers here. Let me put, and when you also strategize this, try to cancel units. So you like, where do I put the liters in cubic centimeters? You put the liter on the bottom because you're getting rid of this liter. And then you do the cubic centimeters, like, do I multiply or divide by the density? In this case, you would multiply because you want to get rid of the cubic centimeters. And then at the end, like, well, this is grams, but I have the answer in kilograms. Asking, this is the given information. It's asking for the mass of the fuel in kilograms. I got to convert back to kilograms. And they're like that. Now, let's say that you did this backwards. You did something like, well, I'm going to start off with fuel on the bottom, and then I'm going to do it backwards. And if you get your answer in 1/kilograms, you then know, like, okay, my units are flipped, which is the nice thing about this. If you've just gotten the answer, but then you have the units flipped, like so density, say instead of density, this one's easy, we're going for mass. Let's say you're doing density and you get your answer in cubic centimeters per gram. You're like, wait a second, density is gram per cubic centimeters. That's nice because you're like, all right, well, I'll just do the math. I'm just going to flip it. So that makes it easy to go back and fix everything. But so keep track of your units and you strategize this such that your units at the end equal the units there. But it's also easier because if your units are wrong, you can kind of go and figure out where you've messed up with the units. So, okay, you go through here, do the dimensional analysis. And since the density has 3 sig figs, you have to report the answer in 3 sig figs. So, which is interesting because, they're very good at measuring how much fuel there are. I'm sorry, how much the volume of the fuel. But then here, I'm surprised. I guess the gas, when you do the gas pump, it goes to the 10th of a gallon. So that would be feasible that you would get it to. a liter or less. So I guess if they were concerned about the mass, but this is one thing with the airplane though, this is, that's a liter of fuel. A liter of fuel is going to be about 5-ish pounds. So that's going to be it's going to be, I'm sorry, that's a gallon. Whoops, what am I saying? Gallon. This is going to be, so you're down about 1,000 liters. That's feasibly, 800 kilogram, or I'm sorry, 800. Yeah, that's 800 kilograms could be. So you would probably have this 800 kilograms is a lot of weight. So you probably would know the density a little bit more accurately for that though. So, but then again, this is a textbook and, versus real world, textbook here, we're trying to train you how to measure this problem. I'm just such a practical person. Like that's 800 kilograms. That's, that could crash the plane. So yeah, you would know it a lot more. But anyways, questions with this one? Nope. All right. I think we're the last one, right? So now the next problem, we're gonna look for solving math, using math to solve things. What's find the radius of a spherical water droplet with a volume of 0.058 cubic centimeters. Volume of the sphere is 4/3 pi r cubed. So you have the volume of a sphere, and so what you do then, you can solve then for the radius. So you can so multiply 3, divide by 4, divide by pi, and you get 3 volume over 4 pi equals r cubed. And then you can solve for r is the cube root of this. And then this is when you just put in your calculator. So you take the volume 0.058 cubic centimeters divided by, 3 times that divided by 4 pi. You take that number and then you take the cube root. One of the things, again, I'm sorry, I don't have my Apple Pencil. You can use the caret symbol and then in parentheses put 1/3. There's the cube root in this, but raising something to the 1/3 power is the same thing as a cube root. So if you do the caret raised to a power and then the parentheses 1/3, that will tell you the answer. So that's an easy way to do it with a scientific calculator. And so this is also like you can kind of, maybe you can do order of magnitude. So if I were to do this in my head, so 3 in pi, if pi is 3.14-ish, 3.14 or 158, I don't know, I want to impress you guys. I had 256, I don't know after that. So, but this would kind of cancel. So you get 0.058 divided by 4. And so let's see here. That's going to be like 64ths. So that's going to be 0.015. So then the cube root of 0.015, I might, I guess it would have to be 0.02. Oh man, that's going to be, I can't do that in my head. I can't figure out what the cube root of that is. So, but I know that if doing this is going to be about 0.015, and I do the cube root of that, I know by math though, that it's going to be a bigger number because when you multiply decimal points, they get smaller and smaller and smaller. So then I would think, okay, if it's going to be cube root of this, I'm expecting to see a number that's bigger than that. Even though I don't have Rain Man ability right now that I could do the cube root. Like, so I would expect to see a number larger than 0.015 or 0.02. And then I get in my calculator, I probably, I'm gonna take this on faith that I put it in correctly. So that's kind of an order of operations, or I'm sorry, order of magnitude sort of calculation you can do in your head and check it. So questions? Okay, I think and we are done with this. And I guess we're moving a little more slowly. I'm going to move on to chapter 2 then. Man, this has been, I don't know how you guys feel. I found out that I really like teaching face-to-face. Hopefully you're feeling that you enjoy coming to class face-to-face, but Man, this has actually been kind of a rough. I can't believe my computers are not talking to each other. It's amazing how you start relying on technology and then, when it betrays you, the betrayal hits you hard. So, right, okay. So questions, anyone, before we move on? Okay, so I think I told you the story that, is it gonna work now? I'm just trying to see if it works. Probably not, okay. I think I told you the story. I one time had a student that never heard of atoms before. I don't think, has anyone here never heard of atoms before? Okay. And another student that, well, that was a student, I was at a party and I think the guy was intoxicated. He was, I don't believe in atoms. And after a while, he was disgruntled about something and he was just trying to mess with me. Well, I was all excited. I was like, oh, I'm a teacher. I can hey, have you ever heard about Dalton before? I heard about the law of conservation of, or I'm sorry, you ever heard about the definite proportions? And I was trying to go through all the logic of where atoms and elements came from. And he's like, no, man, I'm just disgruntled about this. I'm like, oh, I felt bad. I was going to try and convince this person that atoms do exist. So, but I think everyone here kind of, believes in atoms of sort. So we're gonna talk about atoms, and surprise, surprise, they already exist. And we're nice. It's nice right now because we can actually see them. We'll see visible light is longer than the wavelength of visible light, which we'll learn later, is longer than the size of an atom. So we cannot actually see light. I'm sorry, we cannot see atoms using visible light. So this figure here, this is an STM. This is a scanning tunneling microscope. And the way I can just look at this, I'm looking at this, it doesn't even say it's an STM. This one here, well, how can I tell? Because, even here, this one looks like, actually, this could be an AFM. Actually, I have this backwards. Okay, there's two ways of doing this. This one is an STM image. This one actually, I guess I had it backwards. This is an AFM, atomic force microscope. So an STM works. I've kind of drawn it here. You have you have a piece of tungsten, and I have it drawn like a bit of grapes. You have a piece of tungsten, and then this moves. I guess that would still be in This would still be an STM, yeah. And it moves across the surface, and you apply a potential to the surface and the tungsten tip. And when there is electricity going through, that's the signal. You're imaging where an electron cloud is. And one of the issues is that as this tip is moving, and here is your atom. If your tip is here, it's going to have a bit of signal to the atom as it's getting closer, and it kind of gets this roundish image to it. So atoms don't really look like pimples. They're pretty spherical. So they're really kind of spherical. They're not kind of pointy, pimply things. So, but that's just an artifact of the measuring technique. Yeah.
Is it because you can't pinpoint where the electron is? So it's in that area?
Are you talking about the uncertainty principle?
Yes.
This image comes from more the fact that you don't have a straight line when you have an STM tip, which is usually tungsten. You have signal from the side atoms as it's scanning, it's moving. You start to see a signal from the side there. It's not necessarily yes, there is uncertainty in the position of an electron, but that is more the image, the atom getting signal from the side of the tip than the actual point. Because this is a piece of tungsten, it's going to conduct. So it doesn't matter if you're conducting from here or from here. So you just measure the signal of conduction. So this is actually like the where you see electricity and where you don't. as you're scanning. Usually it's linear, it's XYZ, actually just XY. You kind of go back and forth in a pattern like this. And then, but as it's moving, if you have a bunch of grapes, so if this is the SDM tip and here's your atom, you're going to get signal as it's moving. You're going to get signal from here. So if I'm going to do the y-axis, go in here, you get signal, huge signal like that. So
When it goes over, you get the tip.
yeah,
Is the electricity between it?
Yeah.
Okay.
yeah, the potential, but yes, electricity. You're going to see the voltage.
Okay.
So that's an advanced topic, but I'm just trying to tell you, like, why do we have pimples? Because atoms are actually spheres, but it's the imaging technique, and that's kind of cool. It's cool that we can actually image them. So we only had this technology since the 1970s. So before that, I mean, it's kind of like dark matter, right? We just have to take people's word for it. There's matter on the edge of the Milky Way galaxy that we can't see, but it's there, right? But now we can't image it. We don't know what it is. It's just like atoms. Atoms were like, all right, we have these tiny things called atoms, but you can't see them. But there is proof for them. So I'm going to go over some of the proof. I'm going to skip a lot of the history because first of all, we don't have that much time. Secondly, it's kind of cool, but I'm not going to test you on it. That's the other thing. This is not a history of science class. This is a chemistry class. So, and let's talk a little bit about atoms and elements. So what is an atom? What is an element? We mentioned what elements are before in the last class. So elements, we have 118 that we know of. And let's say we take the old trick. We have a bar of carbon. I'm taking that bar of carbon, I'm going to break it in half. I'm going to take that bar of carbon, I'm breaking it in half, and then a smaller bar, I'm going to break that in half. And I'm going to keep on going until I get to a point that if I break it in half, it no longer becomes carbon. And that point is called an atom. So I'm sorry, that element carbon, if I get to a point where if I break it in half, it no longer becomes carbon, that's an atom of carbon. So of course, that only works if you have an even number, right? If you break it in half. But I mean, because carbon, if you break an atom of carbon in half, it becomes lithium. And lithium's a metal. And carbon's a non-metal. They're different elements, different properties, different chemical properties. So that's an atom. And there are some consequences to different atoms, and there's something called the law of definite proportions. So, and the law of multiple proportions. So, for instance, I guess this is the better for definite proportions. So, people observed that, for instance, with sodium and chlorine, if you take 7.7 grams of sodium and 11.9 grams of chlorine, and you react them together, you get 19.6 grams of sodium chloride. So always, always, always. Let's say that instead of 7.7 grams of sodium, and I'm going to put 10 grams of sodium and 11.9 grams of chlorine. I will still get 19.6 grams of sodium chloride, but I'll have extra sodium left over. And let's say I put, so the proportions between the elements sodium and chlorine always give me the same amount of sodium chloride compound. So they notice that with compounds are formed with definite proportions. That's the law of definite proportions. And then there's a law of multiple proportions. So you have carbon dioxide and carbon monoxide. So you have two elements, carbon and oxygen, and you can have one molecule, carbon dioxide, and you can have another molecule, carbon monoxide. So you have two elements, but you form two different compounds that have two very different properties. This is the law of multiple proportions. So you can have two or more elements that form multiple compounds. So maybe you've heard this really lame chemistry joke. Two chemists walk into a bar, or say a restaurant, I'm sorry, I should be a little more proper. They go to a restaurant, and one says, I would like some H2O. The other chemist goes, I would like some H2O too. And the other chemist dies, right? Because H2O2, the joke is it's hydrogen peroxide. So 2 elements, hydrogen, oxygen. So in definite proportions, in a 2-to-1 hydrogen to oxygen ratio, it makes water. Hydrogen, oxygen in a 2-to-2 or 1-to-1. I mean, you can have different type, like we'll talk about this later with the empirical formulas, but 1-to-1 for hydrogen, oxygen ratio, elemental ratio forms peroxide, and it's poisonous, right? So, okay, so Dalton came along, and actually the people that came up with the idea of atoms were the Greeks. They thought that atoms were spherical and unable to be destroyed. They thought they were like the ball pit of the McDonald's. They thought that's what atoms were. So they were these hard things, and different elements had different like balls in them. And of course, the Greeks also thought there were 4 elements: earth, wind, fire, water. They were right about the atoms, wrong about being indestructible, right about spheres, wrong about the number of elements. So, I mean, they were close. They're so close. Dalton came along and said, hey, let's take these things, law of conservation of mass. So law of conservation of mass means in any chemical reaction, actually any physical or chemical process, matter is not created or destroyed. So Dalton, this was already observed, law of conservation of mass. So Dalton came along and said, you know what's going on? Atoms are moving around. The reason why the law of conservation of mass is happening, because elements are not being created or destroyed. Atoms are just moving around in chemical reactions and physical processes. So moving around, and so he made the leap, like, okay, these are atoms, and this is how it works in law of conservation of mass. Law of definite proportions. So we have elements are set in certain proportions for elements, and the atoms then are the smallest unit of an element. And then law of multiple proportions say 2 or more elements can form different compounds, but the ratios of the atoms are different. And what's nice about this class, I don't have to prove this to you. You kind of already understand, like, oh yeah, water is H2O and hydrogen peroxide is H2O2. I've heard of those 2 things. I know they're different. But, of course, in the 19th century, this was pretty crazy stuff. So, okay, so Dalton came along, and I just mentioned what he did. And right now, no one's going to argue that atomic theory doesn't exist, at least usually not in his or her right mind. So Dalton was wrong about some things. Atoms are not indestructible. We've destroyed them. But the rest of the things are more or less right. There are some nuances like isotopes we'll talk about later. Dalton then theorized, hypothesized that atoms were solid and indestructible. Then there was the plum pudding model. Again, I'm just really briefly talking about this. The idea, so a better example of the plum pudding model would be like the blueberry muffin model, if you want an American sort of analogy. So blueberry muffin, you got a big muffin, but every once in a while you get this blueberry in it. So the plum pudding model stated that an atom was this sort of area of positive charge, and then you had these electrons floating inside this area of positive charge. And so kind of like a blueberry muffin, where the muffin is the positive charge and the blueberries are the electrons floating around. And Rutherford came along. I like this story kind of sort of. So Rutherford came along and was like, you know what, I'm gonna figure out if Dalton was right or if the plum pudding model is right. So you can take gold, you can hammer gold down to really thin strips, and then this is actually how most smoke detectors work in a similar fashion. He had an alpha source and then shot alpha particles towards the gold foil, and then had this phosphor detector. And now, mind you, this is the 19th century. So when he did this experiment, and there was an unfortunate grad student who has been lost to history. There's probably can find the guy's name, but Rutherford set up the experiment, told the grad student, like, all right, I want you to go here. And he gave him one of those clickers, like when you go into Costco and they click to see how many people came in. I want you to have a clicker, and every time you see a flash of light, I want you to click this. And so the grad student went around and sat here in the dark, click, 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 all right, an hour's over, click, 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 move another little bit to the left and do this all the way around. And what the data said was that every once in a while there was a deflection, but most of the alpha particles just went right through, maybe scattered more at the end. And so the grad student took all the data, gave it to Rutherford, said, this is wrong, go do it again. So the grad student did it again, got the same result, brought it back to Rutherford. It's like, you're still not doing it right. And the grad student's like, hey, listen, Professor Rutherford, you're there in your tweed jacket, smoking your pipe and drinking coffee with your colleagues. I'm in the dark room. I'm gathering the data. This is right. And the Rutherford's like, maybe the grad student is right. And then the Rutherford, put on his tweed jacket and smoked his pipe and drank some coffee with his colleagues and thought about it like, you know what? Maybe, I know it's my shut up alarm, but maybe what's happening with atoms, you have a really dense positive center. We're going to call that the nucleus. And then the electron cloud around it has basically massless, but most of the atom is empty space. And then, so the radiation can just fly through it, but every once in a while we hit this really dense positive center and that deflects it. So that's the atomic model by Rutherford. We'll pick up there on Wednesday. Hopefully I can figure out my computer by then. So then sorry, I wanted to finish the story. So you guys are free to go. You doing all right, Zoomers? Zoom land? I don't know. What do I call citizens of Zoom?
The Zoomies.
The Zoomies? Works to me.